in the last lecture, I hope you got a fair idea as to how we how the simplex method gets simplified, the calculation part gets simplified when you apply it to the transportation problem. I worked out a problem for you, not the whole of it, but whatever it is. So, now let me look at the issue of degeneracy today, because this also has a role to play. And see here, for example, if you look at this transportation tableau, I have not given the cost, not important. So, this adds up to this, right, 8, 17, 30 and 15 and 15, 30. But what is happening is, when you apply the northwest corner rule, we start from here, then this, but then at this point what happens, essentially here this is, we have made allocation of 15 and 8 plus 7, 15. So, both the row constraint and the column constraint get satisfied. Right. I will refer to this as row constraint, which is actually the supply constraint, and these are your demand constraints. So, anyway, so the column constraint and the supply constraint both get satisfied simultaneously. Okay. And so, you can neither move here or here, like to make a positive allocation. So, therefore, you have to allocate a 0 here or here, you could do it either way, right, and then continue with this 8 and then 7. So, this is where degeneracy will occur, and so this is a necessary condition. So, what we are saying is that so this is a degenerate, the value of the basic variable here is 0, and if you remove, that means if we remove this is what cell 33, if we remove x33, then the basic cells divide into two disjoint cells, divide into two disjoint cells, two disjoint sets, two disjoint right. The first set would contain 1 1, 1 2, 2 2 and 2 3, and the other set will contain the cell 3 4 and 4 4, right. So, you have the thing breaks into two disjoint sets. So, here that means now we say that a necessary, therefore, necessary condition for degeneracy is that there exist subsets C1 of V1 and C2 of V2 such that summation yeah. So, essentially, okay, before I put down the conditions, so what are we saying here is that summation or okay, let me just write it not with a sigma sign. This says that S1 plus S2 is equal to D1 plus D2 plus D3, right. Or also you can say from here that summation, or again no need to write this, S3 plus S4 is equal to D4. So, either way, when it breaks up into two disjoint sets, so obviously this because all the SIs have to add up to DJs. So, once you have this, then you will have also this. So, therefore, what we are saying is that sigma SI I belonging to C1 is equal to summation DJ j belonging to C2. So, you will always be able to find. So, this is a necessary condition, because what will happen is, since to obtain any basic feasible solution, we always we always satisfy either a row constraint or a column constraint, right. So, once this happens, you will be not able to the row and the constraint row and the column constraints will get satisfied simultaneously, and therefore, you will have one less allocation. So, you will have to go for a 0 allocation. So, the logic is simple, right. So, whenever this condition is satisfied, and of course, one can also prove that this is a sufficient condition. So, this is a necessary condition, also it can be shown that this is a sufficient condition, okay, for degeneracy. So, this is what it is. So, therefore, one needs to combat. So, again the question one can ask, or you should ask, is that why not the simple Bland's rule? Yes, Bland's rule can be applied here, and what would be the okay, the rule would be that you enter the first negative Cij, first cell with negative Cij bar, Cij bar is negative, the first one then you encounter, and then for the outgoing variable, remember what we were doing were, because the ratio, when the ratio was tied, the minimum ratio was tied, we were choosing the smallest index. Now here the index are in ij, so obviously you will go for this sum. So whenever when you are doing the minimum ratio and you have a tie, so either of the variable can leave the basis, there are two of them, then you will select the one for which the I plus j is the smallest. So that could be the Bland's rule. So you can apply. So let's just write it down. We can do it, but then I'll give you another practical way of handling degeneracy, which has been proposed. But again, it's your choice. So Bland's rule can be applied. Bland's anti-cycling rules can be applied. Well, why? Because the moment there is degeneracy, you know that cycling can occur, and I'll give you an example also of example where the cycling does occur. Okay, so Bland's anti-cycling rules can be applied, and the rules would be what? But what would the rules? Enter the first non-basic with Cij bar less than 0, right? And second, for the tied leaving variables or outgoing variables, leaving variables, choose the one with smallest I plus j, because here the index is actually I plus j in our sense, right? So this is it. But before let me now show you. So since the condition, the necessary condition tells you that I belonging to C1 is summation dj j belonging to C2. So what was proposed was that you can replace, so replace the SIs to prevent degeneracy, and this is where you would ask the question, why is this enough? But okay, so to prevent degeneracy, replace Si by Si plus epsilon, where epsilon is greater than 0, a proper some proper choice you have to make this for all I varying from 1 to m. Then replace the dj goes to dj for j varying from 1 to n minus 1, and your dn goes to dn plus n epsilon. Remember, the problem has to remain m epsilon. The problem has to remain balanced. So therefore, if you have added m epsilons here, the demand numbers should also be increased by m epsilon. So I just increase the last one by n epsilon, and you can see why this would satisfy this. This would not this choice of this change in the SIs and DJ values will never satisfy this condition. So the changed SIs and DJs will not satisfy this necessary condition for degeneracy, which has also been shown to be sufficient. So therefore, this claim is good enough that the degeneracy would be prevented if you replace the Si by Si plus epsilon, and of course there is a proper choice of epsilon. So you have to say somewhere here for proper choice of epsilon, right? And this of course epsilon is small enough also. It does make the problem solving by hand little cumbersome, but again mostly large problems get solved by the computer. So therefore adding this epsilon is not a big I mean it should not create any problems. Okay. Yes, so maybe we can see it here. Yes, now let me give you an example here. So this is cycling in transportation problem. For quite some time it was believed, because empirically no problem was ever encountered in transportation problem which was cycling because of degeneracy. So people made a claim that maybe it is not necessary to worry about cycling in transportation problem. But then came this example which shows that cycling can occur, and therefore people had to address this problem, right. So let us see, this is a transportation tableau, and of course I have modified the problem. So but essentially the problem comes from Danzig and Thapa. This is linear programming, and I think the editors are Springer. I'll give you the more details later on, but it's a recent book, maybe 3-4 years old. So this book, they have an example. I have modified it a little bit, but it doesn't matter. So now what they say is that if you have this SIs and these DJs, and you see that that condition is satisfied, 1 1, then 3 3, then you have 4 4. So at every step this condition is satisfied, and therefore you have 3 zeros in the basic cells, right. So 3 degenerate values, fine. So this is a basic feasible solution, and starting with this, they said that if you start with this and you just use the normal simplex algorithm, then this is the series of incoming and outgoing variables. For example, in the first iteration, x13 comes in, x23 goes out, then x42 comes in, x12 goes out, and this way. So you see that in the last 4 iterations, what happens is that 23 is coming back again. So 23 is coming back into the basis, then 34 has come into the basis, and 12 has come into the basis. So once these 3 have come back, you will have the same basis, you will have the same set of basic cells, right. So and therefore you will start cycling again, because you started from here with this series of iterations, pivot elements, then you come back to the same thing. Now when you start again, you will keep cycling. So this will create problems, and therefore the idea was that we can start with this one. So let me show you that if you do this, and therefore I should give you the rules also. So that means we would multiply increase these by epsilon, right, and this one will get increased by 4 epsilon. So what are the rules? Rules for preventing cycling. Okay, so rules for preventing cycling. The first one, of course, choose the. So that should not really matter whether you choose the most negative or okay, doesn't matter. Yeah, choose the most negative Cij bar for the entering variable, right, and for the tied outgoing variables, choose the one with smallest coefficient of epsilon, with smallest coefficient of epsilon. Now one would say that how can you be sure that this choice is unique? Well, okay, that can also be proved, and these are the things which you can sit down and try to show, because remember you are adding and subtracting the feasible solutions, because your basis matrix is triangular and the determinant of the triangular matrix basis matrix is 1. So you saw that the right hand side values, all these, they keep different additions and subtractions of these values you get, and so this is not a very difficult thing to show with the smallest coefficient of epsilon. So, try to show, this is a question for you, try to show that this choice of basic variable is unique. Okay. So, this is, I should maybe underline it. It will be good if you can sit down, this will give you a good understanding of the algorithm and of the thing. So, anyway, so for the outgoing variable you will choose the one with the smallest coefficient of epsilon. I will show you 1 or 2 iterations on this to demonstrate that actually this sequence of pivots will get changed because of these rules for preventing cycling, and we will not go beyond that because it will take time otherwise to also to prove that these rules work. They have been shown to work. So, for example, here let us quickly do it. Yes, another note I want to make is that, see, we have been saying that always choose v and 0. Now, this is not necessary because since you are always working with a basic feasible solution, all the constraints are satisfied as equality. So, any dual variable can be chosen as 0, because you need to choose one of them, you need to fix one of them, and then the other remaining m plus n minus 1 dual variables get fixed uniquely. So, it is not necessary, and in fact, a very good thumb rule is, to make your calculations fast, is to choose that vi vj equal to 0 for which column the maximum basic cells, because then immediately, see, if the number of basic cells is large for a certain column, I choose that particular vj to be 0, and then all the ui's get fixed immediately, right, and then the remaining ui's can be determined and the vj's. So, it is not necessary that we should always choose vn equal to 0, but anyway, in this case, yeah, see, for example, here vn is there is only one entry here. So, there is no point choosing. So, I can choose any one of them to be 0. So, let me say that this is 0, or I could have chosen this u1 to be 0. Any one of the dual variables you can fix, and then the remaining ones get fixed uniquely. Okay. So, this is the idea. So, therefore, let me, if I choose this as 0, so what I am saying is that, see, this will be 9 and this will be 1. So, these two get fixed, 11, right. And now, let us quickly do it. Once you have this 7, so this should be minus 2, right, because 9 minus 2 should be is equal to 7, right. Once this is minus 2, this will be 7, because 7 minus 2 is 5. This is this, then this will be minus 4. Yes, and then from here this is 13, so this should be 2. Once that is 2, this should be 15. Okay. So, let us now compute the relative prices, which is minus 2 here, right, 5 minus 7, then 11 minus 9, which is 2, and here this is 9 minus 5, which is 4, and this is 15 minus 11, which is also 4, this is 7 minus 7, 0, then 9, so this is minus 2. The last row you have to compute here, this difference is 11. So, 13 minus 11 is 2, okay, and then this is also 13. So, this is 0, and this is 15. So, this is minus 2. Obviously, the solution is not optimal because you have minus entries here for the C bars and C bar ij's, and therefore, you can improve. So, then this is 15 or 2 17, and so this is 0. Okay. Oh, so you have a, sorry, you have a, this has to be 0 because this is a basic cell, you see. So, the computations are okay. This was a basic cell, I did not show it. Okay. So, now I want to give you this rules for preventing cycling, another new method, and this is the perturbation method that is called. Of course, for the general linear programming problem, simplex algorithm, I had given you rules, Bland's anti-cycling rules, but I want to show you that because the structure is special structure here, you can get another simplification here, and this is choose the most negative C I j bar for the entering variable, okay, C I j bar. And so, the first rule is the same as that for the simplex algorithm, and then for the tied outgoing variable, because you see the tie occurs in the minimum ratio, and so you have to decide which one is the outgoing variable. That choice may not be unique in the simplex algorithm. So, here we say that you choose the one with the smallest coefficient of epsilon. So, now I will explain. So, therefore, the idea is that you perturb the right hand side. So, 1 plus epsilon, 2 plus epsilon, 1 plus epsilon and 2 plus epsilon, and here this is 4 epsilon. Okay. Because the row sum and the SIs and the DJs must add up to the same number. So, the perturbation has to be to maintain that balance. So, this is again a balanced transportation problem, and we said that the choice of epsilon has to be appropriate, and I will show you in the process of showing you how the rules have to be applied. So, you see, if you want to now update your this thing, then here I can make this epsilon, right. And okay, let me also point out that this is not the only way of perturbing the SIs and DJs. You can do it differently also. Let us, you can add 1 plus epsilon, 2 plus epsilon here, and then add 4 epsilon here. So, you can do it either way, fine. So, this becomes epsilon, and then since this is 2, so you have to have this one, you have to update this one, and so this becomes 2 minus epsilon. Okay. And since you have updated this, and this here is 2 plus epsilon, so you need to change this, which will become 2 epsilon. Okay. So, let us quickly do it. Now, this is again intact, this is 1. So, I have to reduce this by 1 minus 2 epsilon, okay. And then this will be 3 epsilon, because 1 plus epsilon, right, and then here this will become plus epsilon. So, now all the numbers match, right, the row sums and the column sums, everything is okay. And here you see, you immediately see that your epsilon cannot be bigger than half, because you do not want this number to be negative. Okay. So, this is what we mean by appropriateness. So, essentially you say that epsilon is small enough, so that at no iteration you get a infeasible solution. Okay. So, now this is what it is, and you have to choose the most negative incoming variable. So, since all these C bars are minus 2, I can easily take this to be the incoming variable. Okay. But one could choose any one of these, and so let me choose this one, and then so you will form a theta loop, and this will be this. The theta loop can be easily. So, as I said that for small problems when you are doing by hand, you can use any ad hoc method to locate the theta loop. So, here this goes by theta, this goes by minus theta, plus theta, minus theta, and here we will be governed by. So, of course, there is no tie as such, but here you see to maintain feasibility you will choose theta to be equal to epsilon, because here this is 2 epsilon. So, this will remain positive. So, now your new solution, that means I update it, and so this is the incoming variable, and here this will become. So, you have removed this. So, this is 0, this is gone out, and this one now becomes epsilon. This one you will add epsilon, because the row column sum has to be intact. So, this is 2, right, and then here this is minus theta. So, this is epsilon, right. This is your new basic feasible solution, and some of these UIs and VJs will change, and you need to okay. So, you continue with the simplex algorithm, but yeah, lack of time, and so therefore, I will not go through, but it just happens that now when you recompute the C bars, the next iteration you will land up with a optimal solution. Okay. So, all the Cij bars, I think one more iteration is needed, and after that if you follow these rules, then you will get a optimal solution. And this is the point we want to make here, is that Bland's anticycling rules have been known to be to work very slowly. So, they are not at all suitable for combating degeneracy or cycling in the transportation problem, and taking the advantage. So, the epsilon perturbation methods have proved to be very reasonable, and they get you, I mean, of course, what you can do is finish this with the epsilon perturbation method, and then try to apply Bland's anti-cycling rules to this problem and just see. And of course, one problem is not any criteria for judging which is a better method, but you will see that certainly Bland's rule will take you for more iterations than what you had to go through for the perturbation method. Okay. So, and okay, now interesting result by Orden, and let me just give you the yeah, I want to point out Orden in 1956. Okay, and this is the journal's name is Management Science. This is number 2, and this is 276 to 285 pages, right. So, in this journal he had this article where he has further improved on the perturbation method, and he says that so here, of course, here what they are saying is that if so he says that if SI, I will just quote the theorem by Orden, which says I varying from 1 to m, and dj's are the demands, 1 to n are integers, of course, positive integers are positive integers, and if dj are replaced by dj plus 1 by n. So, you see here he is perturbing the this thing, each of the demand points demands, and then he will do the. So, if dj goes to dj plus 1 and si, oh sorry, and this is okay, I should say for all j, and sm goes to sm plus 1, right, because n of these. So, then the total thing would be n into 1 by n, which is 1. So, you perturb the last supply point supply as sm plus 1, right. Then every basic feasible solution of the new problem is non-degenerate, and the corresponding basic solution of the for the original problem is always feasible. Okay. Before I comment on this. So, anyway, now we know that once we have got an optimal solution with the perturbed problem, then I will, to get the optimal solution for the original problem, I will just put epsilon equal to 0, and because I have maintained feasibility, my choice. So, that was the point, that the choice of epsilon would have been appropriate. So, that you never got an infeasible solution when you put. So, therefore, what you get when you put epsilon equal to 0 would be again a feasible solution and an optimal solution for the original problem. Now, Orden says that no, you do not have to worry about the appropriateness of epsilon, you just perturbed each of the dj's by 1 by n, and then sm by sm plus 1, and in the case that what we did, we actually perturbed each si by so we if you follow Orden's rule, then we would perturb each si by 1 by m, and then the last dn Dn would be perturbed by 1. So, that will be the difference only otherwise. So, then he is saying that you just go on with this perturbed values of dj's and si's and then use the transportation algorithm, and for finally what you get. And so, at each iteration you will be getting a non-degenerate solution. That means, none of your basic variables will become 0. So, this is important. Okay. And so, therefore, once if you do not have any if you can maintain non-degeneracy all the time, then there is no question of cycling, and therefore, it takes care of. So, it prevents cycling, and that the original problem will always be feasible. So, this is what Auden's result says, and you can try it out. Maybe with the same problem you can use this perturbation and then see that you will always get degenerate solution at each iteration, and you will be able to, right. Okay. Fine. So, yeah. So, now the next thing that we were talking about after taking care of degeneracy is sensitivity analysis. Sensitivity analysis we will continue with, and here I want to say that suppose, see, the idea here is that suppose I change one of these SIs or the DJs, how do I, the same question that we posed for the linear programming problem in general was that can I somehow also I either try to find out whether the current solution is optimal for the changes that I have made in the SI or DJ one at a time. Of course, we will consider that, or can I get a new basic feasible solution which is optimal. So, this is the whole idea. And now, here for example, the issues are different in the sense that suppose I change this one to 9 plus 1, and see, we always do marginal analysis, and since I am dealing with integers, you see I can think of changing the SIs or a DJ by at least just 1 in number 1, because the solution will, since the solutions are at each iteration integer valued. Okay. So, the idea is that this 9 plus 1, I have more amount available here, and then the question asked is, will the cost change? That means, can the cost go down? That is the whole concern. And why? Because you see, it is possible that from this particular source, the cost of sending the material to different markets may be cheaper, or the routes, some of the routes that you are using in your optimal solution, the cost may be cheaper, and so you would like to send more from here and then show the surplus elsewhere. That means you may not use the whole amount from another source from where the cost of sending the material to different markets is more expensive. Okay. So, this is the consideration, and these are the kind of things which you can see here, and therefore, for the transportation problem this kind of sensitivity acquires lot of meaning. So, here let me just consider this case of that say this particular S2 has gone up to 10 units. So, my problem has now become unbalanced, right. The problem is unbalanced. The problem is unbalanced, right. Let me just quickly say that means your SI's primes are there, and you have the same DJs. I have not changed them, and here also only one of the SI's has changed, and summation SI prime I varying from 1 to m is strictly greater than summation DJ j varying from 1 to n. So, that means that your constraints, for example, now since you are not and you do not know. So, the question asked is where will the surplus show. So, therefore, I do not know which constraint would be satisfied as equality and which will be the supply constraints satisfied as inequality, right. So, x I j varying from 1 to n would be less than or equal to S I prime, I am saying, because I do not know which one, right, and then summation x I j summation over I varying from 1 to m is equal to d j. So, I have to meet the demand constraints, right, j varying from 1 to n, right. So, then as usual, because we have a less than or equal to kind constraint, we will add slack variables, and what it means here is that you simply add a market. see when I add, because I will be adding constraints here to the supply this thing. So, therefore, for each row there is a variable, and since it is playing a role of a 0 variable, that means I am adding a virtual market or an artificial market where the surplus will show, but actually there is nothing like that, right. So, wherever I am not using the complete supply, that is where the surplus will show. That means, the numbers will not add up to. So, somewhere these numbers will not add up to that particular number wherever the supply the surplus has to show, right. So, you are adding, and therefore, now your constraints become x I j, j varying from 1 to n plus 1. I am not writing xs x I s and so on, so it is n plus 1. So, then this becomes s I prime, right, I varying from 1 to m, and summation x I j, I varying from 1 to m is equal to d j, and here j varies from 1 to n plus 1, and so you know that your d n plus 1 is equal to 1, the difference between sigma s I prime minus sigma d j, because I have just increased the one supply by more than 1, right. And now you can see that immediately, because this market, see this column is the new column. So, in the dual constraint you will simply have constraints added. So, that the added constraint to the dual problem is right. So, therefore, just since the one column has added, you can see it from here also, but I will quickly do it this way. So, you have now you have a new this thing here, you will have a V n, right. We will compute the dual variables also, I will quickly do it. So, anyway, what you will have now here is u 1 plus V n less than or equal to 0, because the corresponding C I j's are zeros. So, then this will be u 2 plus V n less than or equal to 0, u 3 plus V n less than or equal to 0, and u 4 plus V n is less than or equal to 0. So, let us first show you the calculations of the u i's and v j's, which I have already done here. Yeah. So, this comes out to be minus 1, 2, 4, 5 and 5, okay. And then this is 2, 1, 0, minus 1. So, you can do this by put this through 0, and then you can, because again, so I am using the rule that you have the maximum number of basic cells here. So, put this 0, and then you can make the computations, right. Okay. So, essentially in the dual, and remember dual feasibility implies primal optimality. So, here what do you see here? Oh, V n I should write, okay. Okay, I am sorry. If I am doing for the general thing, then I should have said this is up to okay, dot dot dot, and this is u m, fine, yeah, dot dot dot. Just please take it that way, fine. So, then what we are saying is that your V n is less than. So, if I choose my V n to be equal to minus max u I varying from or 1 less than or equal to I less than or equal to m, then you see with choice of V n, then all these constraints will be satisfied, right. Once you have V n chosen like this, then you see, and say suppose this is equal to minus u p, suppose, right. So, then you have V n plus u p equal to 0, and so by complementary slackness condition, this implies that your x p n should be equal to now again sorry for the this thing, this should be n plus 1. I have written V n here, that is a mistake, this is V n plus 1, and for this particular problem 1, 2, 3, 4, 5, so that will be 6. Yeah, sorry. So, I am glad I got the mistake right now. So, this will be plus 1 plus 1, right. So, x p n plus 1 will be positive, right. So, if you have a feasible solution for the primal, you have a feasible solution for the dual, and they satisfy complementary slackness conditions, then you know that that solution is optimal. So, here that means for the expanded problem, when you have transformed the unbalanced problem to a balanced one, then you have this the extra dual constraints are these, and so by choice of v n plus 1, here again v n plus 1 equal to this, you see that your new solution will satisfy. So, I do not have to change the other ui's or the other vj's, simply choose v n plus 1 to be equal to this, and then you see that the constraint is satisfied, this particular is satisfied as equality, and so your x p n plus 1 can be positive. That means, the surplus will show in the pth row or the pth source. So, that means, if you had changed, see here I did not say, yeah. So, for example, here we were saying that if S I has gone up to S I plus 1, this was our mandate, then the surplus will show at this pth source, right, and p corresponds to this number here. So, in our particular case, let us just look at it this way. So, this has gone up to, so your I is 2, S 2 has gone up to 10, and the maximum of this is 2. So, that means your u I is max of u r, okay, 1 less than or equal to r less than or equal to 4. So, u I is this, and therefore, no, why am I u 1, this is u 1, okay, which is equal to 2. Okay. So, that means, what it says is that you use all the supply that is available here, and the surplus should show here. So, that means, how do I transform my new get the new solution? So, that means, this will go up by 1, and because the column sum has to remain intact. So, this will be minus 1. So, that means, here on this route I will only be sending 8 units from this source. So, 1 extra unit will be left here, and the extra unit that was added here got used up, because you see the difference in the cost, right. So, this particular route you charges 5 units 5 rupees, and this one charges 6 rupees. So, therefore, that is the difference, and you can from here whichever way you want to do it. This is you can say compute the difference in the cost, and for example, how will you do it? Yeah. So, you can, because this particular route the cost has gone up, and this. So, therefore, the difference in the cost you will compute difference in cost is 5 minus 6 this way, right. And if you want to look at the dual, then what is happening? Say your dual objective function. Dual objective function, you have summation S I prime u I varying from 1 to m plus summation v j d j varying from 1 to n plus 1, right. And what is happening is that your so this nothing is changing here, because now I am referring to the you should I do not have to take it to n plus 1, or would it be, yeah, we do not have to take it to n plus 1, because I am referring to the original problem. So, the original problem I am trying to compute the cost in the difference in the cost. So, what is happening is that your essentially when we do this, my S 2 went up. So, this that means the change in the cost will be so the change in the dual objective function. So, this was your u 2, which is 1 into 1, because S 2 went up by 1, and this came down by 1. So, the difference is minus 2 u 2 into 1, because S 1 came down by 1, and the cost and the corresponding u 1 is 2. So, I subtract this, and this becomes minus 1. So, the two costs match, and therefore, yeah. So, now I have just shown you how to tackle the change in the SI. If you change one of the DJs, then you see that means you will have extra demand, and that means for here you will have to yeah. So, that means in this case we are only considering the changes in the SIs, because the moment you have a increase in the dj and you do not change the SIs, then your problem is not feasible, because you are allowing, or either you should then have the possibility that if some particular demand is going down, then some other demand should go down. If some particular demand is going up, then some other demand should go down, so that you can handle the problem feasible. Or the other case which I will look at with you now is that you simultaneously change a particular supply point and a particular demand point, because see, remember, for feasibility you have to have either a balance problem, and if you want to satisfy the demand constraints as equality, then if you raise one of the demands, then some other demand must go down, or you allow demand constraints to be satisfied as inequality, and in that case you will have to then add surplus variables, and that will require. But surely with the knowledge that you have gained here about the how you transform the simplex algorithm to the transportation problem, you should be able to handle it, but that will require separate treatment, okay, which I have not considered here. So, the next topic that I want to look at is when you are changing a particular, so now see a pair. So, that means now I want to look at changes in a pair SI dj, right. So, that means I am saying that a particular SI goes to SI plus 1 and dj goes to dj plus 1. So, now the problem remains balanced, and it is just a question of adapting the current solution to the changed supply and demand, right. So, here the idea is that to find a path, from a basic cell in find a path from a basic cell in row I to a basic cell in column j. So, if I can find this, then I can accommodate the changes in SI and dj. This is the whole idea. Okay. So, yeah. So, let us see what will I do. So, that means, for example, if I have yeah. So, what we are saying is that say consider the cell I R1, a basic cell in row I, right. Now, see, because only SI has changed and dj has changed. So, the demand for column R1 has not changed. So, I should be, so when I choose this cell, because I have to raise SI has gone to SI plus 1. So, I can use, that means this particular value xi R1 will go up to go up by 1. So, therefore, when I choose this cell, the basic cell in row I, such that there is a basic cell in column R1. See, remember, the basic cells are connected, yes, and I have to get back to this one particular property, which I will do right now. So, what is saying is that you should be able to move to a column along the R1, because the demand for row column R1 has not changed. So, there is a basic cell in column R1, say what do you want to say here, something like I2 R1, right. Now, here again if I2 is not equal to okay, no, so I2 is not equal to, and I do not have to worry about that. Okay. So, say this thing, right. Now, SR2 has not changed. So, there is a basic column, basic cell in row R2. So, the idea is that you just keep on moving. So, to find a path, you have to find a path from a basic cell in row I to a basic cell in column J. This is the whole idea, right. So, cell in row, and then so go on moving. So, keep moving till a basic cell in column J is found. Okay. So, we said that so you find a path like this, and therefore, and then we will alternatively say, for example, let me keep this as this, and suppose I increase this to 1. So, the idea here is I have to look for a cell in this row. So, there are 2 of them, but since there is nothing here, so therefore, I cannot increasing this, then I will not be able to balance it with any decrease in a basic cell. So, I simply do this one here, and okay, in this case we are just lucky because this is 6 plus 1 and this is also. So, the whole total here goes up, forget about this, right. So, here this is 13 and that is 10, right. But suppose you had changed this to plus 1. So, suppose this went up to plus 1 and this again was this, then what I am suggesting is that I will have to look for a basic cell here. Okay. So, the basic cell, see for example, again I cannot choose this, or I can, okay, fine, I can choose this because there is a basic cell here. So, that means if I increase this by 1, I will decrease this by 1, and then I will come here because this row is intact. So, this will become plus 1, and then you see from here I can then increase. So, this is, but that is it. So, so now we are talking about this as 24 will become 25 and this is 13. So, then you see this is now. So, therefore, I have found a path with the cell starting in row 3, and then I went up here, and this, so this row sum is intact and this column is become. So, the whole idea that you find a basic cell in the row in which the thing has gone up, the supply has gone up, and then connect it with a path, and you will always be able to find a path. So, this is a comment I wanted to make, is that I defined for you a set of basic cells, and then I said that there will be. So, what we want to say is that a basic cell will always be at least one basic cell will be present in a row or a column for the whole array, which you can see by connectivity, because if I want to take any non-basic cell in a column, and if there is no basic cell present in that column, then or in that row, then I cannot find a path from that basic non-basic cell to connect it to the basic cells, because I need the number, and that when you have a basis, you will always be able to find linear combination of the basic cell basic columns, so to express that non-basic column, and so same applies to a non-basic cell, and therefore, every basic cell a basic cell will always be present in every row and column, and so the connectivity is there, and this the technique that we are telling you, you will be able to find a path from the row for which the supply has gone up to demand point for which the demand has gone up. Okay. Now, the other thing is cost. So, changes in cost. I want to talk about changes in cost, and here the treatment is straightforward, because again you have the calculations you can do directly on the tableau here on the array, and what I am saying is that we can just get rid of this. Okay. So, this will come back to the thing. I have computed the C bars here, and what we are saying is that if I j is a non-basic cell, right, and your C I j goes up to C I j plus delta I j, then it is very straightforward, because the new dual constraint or the optimality criterion, dual constraint is u I plus V j, so C plus C I j, and so here it is delta I j. Why is it should happen that yeah, this is less than, you say that, oh, okay, let me, yeah, what you say is that your ui plus vj should be less than or equal to cij plus delta ij, right. So, this implies that your delta ij should be greater than or equal to delta ij ui plus vj minus cij, which is equal to minus of cij minus ui minus vj, which is minus cij bar. So, that is it. If your delta ij, if the increase in the value of the cij is greater than or equal to this, then your current solution remains optimal. And so, you can just read off the numbers from here. For example, this cannot, so the increase if is more than -1, here the increase is more than -3, then your current solution remains optimal, and you can read it for the others. Now, for the non-basic variables, it becomes a little complicated for the basic variables. So, this is a non-basic cell. Now, suppose ij is a basic cell. Okay. If it is a basic cell and your cij plus delta, the increase is by delta ij here, then you see your ui's and vj's will also change, and so then you will get an interval for delta ij. So, say for example, here if this number goes up to delta, so this is delta 1 3, okay, and you can quickly compute. I will just show you the numbers here, because otherwise it will take time. So, this is 2 minus delta, okay, then 5 minus delta, and this is also 5 minus delta. Okay, then here it will become delta plus 2. Okay, I am writing delta just to save time, because otherwise it should be delta 1 3. So, this what we are writing here should be delta 1 3, and then this becomes delta here plus delta, and this is plus delta here. So, this is your new values, and you see what happens is you can compute it for others. It turns out that this comes out to be minus delta. So, right now I am taking delta to be, if I am taking delta to be a positive number, so that means here I am saying that delta ij, which I am taking to be delta, is positive, then you see this will be, this will not be feasible, this will not be optimal, the current solution will not be optimal. So, if you are asking a question, what happens when my particular C13 goes up to 6 plus delta 1 3, then is there a limit for delta 3, so that my current solution remains optimal. You see, I have computed the, once you change Cij for a basic cell, then 6 plus delta this becomes, and because your ui's and vj's depend on the basic cells. So, they see the calculations change, all the C bars, almost all the C bars except for these two change, right. So, 1 minus delta, 3 minus delta, and so on, right. So, that means here you will essentially, so I am talking in general that you would have an interval for delta, and if your delta is in that interval, then the current solution will remain optimal. And but in this case, you see what is happening is that this particular number is coming out to be minus delta. So, that means if for delta, or okay, I am using delta 1 3 is in the interval minus infinity 0. See, then the current solution will remain optimal. That means, if delta 1, if I take it to be negative, see here I said when it is positive, then I mean this will be negative. So, this will remain positive if your delta 1 3 is in the interval minus infinity to 0. And the moment your delta becomes positive, then this is a negative number, right, and then this will be a candidate for coming into the basis, because you see that from here, otherwise all other values remain non-negative for like delta less than or equal to 1, delta less than or equal to 2, and so on. So, this will be the first variable to come into the basis, and you can then enter this into the basis and continue with your optimal solution. Right. Otherwise, when you get an interval, say for example, if you get an interval for I can use the number, let us say some bij and aij. So, you will get an interval like this, and for delta ij greater than
Bij or less than Aij, the corresponding cell will be a candidate for entering the basis, and then you can continue with your simplex algorithm to get a new optimal solution. So, you can handle the changes in the costs here, and I have also shown you how to handle the changes in the SIs and also the changes in SIs and DJs. Now, the changes in DJs, yes, requires a little special treatment, which hopefully maybe I will mention sometime later on. Okay.